What's up, meat wagons? Today, we're going to talk about factoring binomials. Binomials are kind of a different beast. They're kind of like simple factoring, actually. You kind of just look at them until you know the answer, and then you write it down, right? So we're going to look at two specific types of binomials today. We're going to look at sum and difference of cubes. I'm going to give you a formula that we can use to factor these. And then we're going to look at differences of squares. These ones are pretty easy. These ones students tend to not be a huge fan of because there's a formula and it's not the same every single time. You have to use your brain a little bit and think about the answer. And I know how you guys feel about thinking. It makes your head hurt. So I'll do my best to simplify it. But realize this is part of school, and you're going to have to use your brain a little bit. It's not FIFA. You can't just feel your way through it. So let me go ahead and give you some general explanation about the way these things be, and then I'll do some examples with you. So as you can tell from the title, since we're looking at sums and differences of cubes and differences of squares, it would be very beneficial for you to know all your perfect squares and cubes up to a certain point, right? Now, I'm not your mom, and I can't make you do anything. But this is like trying to get through elementary school without learning your multiplication table. You can probably make it. You're here, right? But it makes it a lot harder, and then you're going to give yourself self-esteem issues, and you're going to, I'm not any good at math. I can't even multiply. Well, have you tried practicing, So this is one of those things. You can definitely do these problems without having a working knowledge of perfect squares, but it's a lot easier if you did. You know what I mean? So perfect squares are just what do you get when you multiply a number to itself, right? These are all those numbers that you kind of had an inkling that were special or easy to memorize when you were in third grade and you did your time multiplication test. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. So here's a list of them all the way up to 18. I'm not going to promise they don't go past 18, but here's a list up to 18, right? I think usually the highest they go is maybe 16-ish, but again, I'm not going to make any promises. The next set, and this is a set that you're probably not as familiar with, are the perfect cubes. So this is what you get when you multiply a number to itself 3 times instead of 2 times like over here. So for instance, 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27, and so on. You're going to notice that these numbers get a whole heck of a lot bigger, a lot faster than these numbers over here. So if you look at 6, we're at 216. That's bigger than 14 squared. So they get big pretty quick. But here's a list of most of the common ones you're going to see in this class. Because you have a very benevolent math teacher, I try and keep the numbers in a manageable range for you, right? I could be a real jerk and give you something real crazy, right? We could do whatever the heck 57 squared is, and we could do 102 cubed. But these numbers get so big that they're just unmanageable, and I have to do the examples and help you with the homework. So kind of for my own sanity, we'll keep them in this range as best we can. But again, no promises. Okay, so my advice right now is write these down. Maybe practice with your dog. I don't know, whatever floats your boat. All right, let's talk about difference of squares. So difference is the math word for subtracting. Of squares just means you're taking something squared and subtracting something else squared. Okay. Our job is going to be to find A and B, and then we're going to plug it into this formula. This is the answer, You just have to find A and B and then fill it in. So what you're going to do is you're going to go, oh, look, that looks like something squared. To find A, we need to get rid of the squared. So how do you cancel a squared? Oh, you just take a square root. Same thing with B. You're going to completely ignore the negative. It's just part of the equation. You're going to take a square root of the thing after the negative, like so, right? That will tell us A and B. Then we'll be able to fill out our difference of squares. Okay, so let's go ahead and do a few examples. And then there's a couple in here that have some really nice, what's the word for it? Like tricks to them, so that I can warn you about some weird stuff that you're going to see. So I'm trying my best to preempt any problems, but I'm only human. All right, so let's look at number 1 here. We have x squared. That's a big tip-off. And then 1. 1's on this list. It's a perfect square. So what we're going to do to find A and B is we're going to take a square root of this and a square root of this. The square root of x squared cancels the squared. So it's just x. So A is going to be x, the A value here and here. And then B is going to be the square root of 1 is 1. Okay. Now we're going to fill in this formula. So A minus B, so x minus 1, and then A plus B, x plus 1. And this is the answer. There you go, you did it. And just for this one alone, I'm going to foil this back together just to kind of prove to you that you get this and show you why it gets smaller instead of bigger and scarier. So let's foil it. X times x is x squared. X times 1 is 1x. Negative 1 times x is negative 1x. And negative 1 times 1 is negative 1. Now we combine the like terms in the middle, but lo and behold, 1x minus 1x cancels and they go away. So you just get these two outside terms, x squared minus 1. Oh, look, that's the original problem up there. So we did it right. These have a special name. These are called conjugates. That's not going to be on the test or anything, but they have a name, so you might as well like hear it, you know. So there you go. That's our first example. Okay. Let's move over here to number 2. Before we dive into this, right, you're going to say, Mr. Barton, 7 is not a perfect square. That's a hint to you that you're supposed to do something to this first before we try and apply this difference of squares idea. The thing you're supposed to do here beforehand is take out the GCF. So if we can, we want to remove a GCF first because it makes the number smaller and then hopefully easier to handle. So in case you're not aware, 7 goes into 175. So let's divide both these by 7. And we're going to put our GCF on the outside, right? It's our little brother. We can't lose it. These cancel. X squared. 7 goes into 175 25 times. Now look. X squared, well, it's got squared in the name, right? So it's a perfect square. 25, what number times itself is 25? Oh yeah, 5. So 25 is a perfect square also. So now we're going to find A and B, and then we're going to fill out this formula. So we take a square root of both of these terms. So A, square root of x squared is x. B, square root of 25 is 5. So let's bring down our little brother, the 7 first. Then we're going to have 2 sets of parentheses. One with a plus, one with a minus. Mr. Barton, it's in a different order up there. It doesn't matter. Multiplication is commutative, and the order doesn't matter. So it's going to be x, or rather a plus b, so x plus 5, and a minus b, so x minus 5. And that's your answer. Pretty easy, right? All right. I've got a total of 6 of these examples for you, and then we'll go talk about cubes, which are a little bit trickier. Again, 12 and 48 are not perfect squares. They're not on this list here. So that's a hint that we can take out a GCF. It's 12. So let's take out 12. 12 goes in front. So we have x squared minus 4. Now these are perfect squares. We can take a square root. So a is x and b is 2. Bring down your GCF. Parentheses, parentheses. Put a plus in one, a minus in the other. Fill in a and b. X and 2, x and 2. You're done. That's the answer. Good? Not too bad? All right. Oh, look, a big number. Oh, well, it's on the list. Don't worry. So, we don't have a GCF here. We can just go ahead. Let me erase some of this so we can see what we're doing. There's no GCF, so we just start by taking square roots. So a is still x, because the squared and square root cancel. B, if you don't know the square root of 256, I don't really blame you. You can go look on that list that your wonderful math teacher gave you. 16 squared is 256. So the square root of 256 is 16. So B is 16. Now we put parentheses, plus in the middle of one, minus in the other. Fill in a and b. X, 16, x, 16. All right. 2 more, and these are like the last possible ways I can think to try and trick you, but I'm going to show you the trick so that it's not a trick when it comes to your homework. Okay. Oh no, that's not squared, that's a 4. Oh well. Let me show you something. X squared times x squared. When you multiply, you add the exponents. So x squared times x squared is x to the 4th. So that means the square root of x to the 4th is x squared. So a, instead of being x this time, is x squared. And the square root of 1 is still 1. Repeat our process. Parentheses, plus in one, minus in another. X squared plus 1, x squared minus 1. Hold on, though. We're not done. Look at this. This is something squared minus a perfect square. This is difference of squares again. So we have to factor this one more time using the same method we've been doing this whole lesson. So this one is a plus. That means it's safe. You can't factor it. So we're going to go ahead and just bring this one down. This is x squared plus 1 still. This one, we're going to take our square roots again. Square root, square root. A is x. B is 1. Split it up into 2 sets of parentheses. Plus in one, minus in the other. Fill in a and b. Good? That's your answer. It's all factored up. Okay. 6 is the last one. Now we have a number here. And you should know, hopefully, because you know your times tables, because you're in high school now, that 36 and 25 do not share any factors. So, what do? We just go ahead and repeat the same process. 36 is a perfect square. 25 is a perfect square. So the process will work on this. We're going to take a square root, take a square root. Now a, what's the square root of 36? It's 6. What's the square root of x to the 4th? Well, we just saw over here that it's x squared. So a is 6x squared. B, the square root of 25 is 5. Parentheses. Oh, I changed the order. It's fine. It doesn't matter. 6x squared minus 5. 6x squared plus 5. Oh no, Mr. Barton, but Mr. Barton, hold on. We have an x squared and there's a minus. Okay, but 5 and 6 are not perfect squares. So while you're right, we do have an x squared and a minus. That's not enough. We have to have a perfect square here. And if there's a coefficient, it has to be a perfect square. So even though this one kind of looks like we could do perfect squares again, because 5 and 6 aren't perfect squares, it's stuck this way. And thank goodness for you, you're done. And that's the answer. All right, let's go talk about sums and differences of cubes. So now, just like you can't take a square root of a negative number, but you can take a cube root of a negative number, we can't do a sum of squares, right? This thing doesn't exist. This isn't a thing. We can do a sum of cubes, though. So we're going to do the same process, except now instead of having a nice formula like a minus b and a plus b, we have a slightly more grown-up formula. So let's take a look at it and talk about why some people call it the SOAP formula. So if we have something cubed plus or minus something else cubed, we can factor that. When we do that, we're going to get two sets of parentheses again, this set and this set. The first one will be A and B, and the sign in the middle will be S for the same sign as whatever's in the problem. So if it's a cubed plus a cubed, it'll be A plus B. If it's a cubed minus a cubed, it'll be A minus B, because this first sign in the smaller parentheses should be the same as what's in the problem. Okay. Then we have a slightly more complex set of parentheses, but there's a pattern. It's two A's, one of each, two B's. Not a bad pattern. These signs follow a pattern too. The sign between a squared and ab is the opposite sign as what's in the original problem. So because this is a plus, minus sign. Because this is a minus, plus sign. Then this last sign here, before the b squared, is just always positive. So same, opposite, always positive gives us what I affectionately call the SOAP formula. Not too bad, okay? I'm going to show you how to apply this. Again, we're going to start by finding A and B, and then we're just going to plug into the formula. Okay, so let's do 4 examples, and then we'll look at some with GCFs. Hint, we're just going to take the GCF out first, and then it'll be easy peasy lemon peasy. All right, so let's start with a nice baby one. X cubed, and then 1 is a perfect cubed in addition to a perfect square. It's actually a perfect everything. 1 to any power is 1. Even 0, interestingly enough. So what we're going to do is we're going to take a cube root of both of these to find A and B. So the cube root cancels the cubed, just like square roots cancel squareds. And then the cube root of 1 is 1. So A is X and B is 1. Now we're going to use our SOAP formula. So the first set of parentheses is A and B, and it's SOAP S, same sign as what's in the problem, so minus. Then we have a bigger set of parentheses. It's going to be A squared. So X times X is X squared. SOAP SO, opposite of what's in the problem. So we're going to put a plus sign because the problem has a minus. A times B in the middle. So X times 1 is just X. OP, AP at the end. Always positive. B squared. 1 times 1 is 1. And that's the answer. All right, let's try a little bit harder one with some bigger numbers. Nah, that's gonna be hard to see. Let's do blue. All right, cube roots to find A and B. A, cube root cancels the cubed, is X. Cube root of 8, go look at that handy dandy chart that I gave you. erase all the stuff I scribbled on. Find 8. Oh, there's 8. 8 is the perfect cube of 2, so the cube root of 8 is dos. So B is 2. Now we use the SOAP formula. Parentheses, A and B. Same sign as what's in the problem. Next, A squared. X times X is X squared. Opposite sign. So this could be a plus. A times B, so 2 times X is 2X. Always positive. B squared. 2 times 2 is 4. That's your answer. All right. 2 more, and I'm going to modify this one a teeny tiny bit. Okay. Let's do green. Cube root. Cube root. A is cancel, cancel. X. B, we go look at the chart. The cube root of 64 is 4. SOAP formula. Put in A and B. Same sign as what's in the problem. Parentheses. A squared, 2 A's, is X squared. Opposite, so that's going to be minus. A times B is 4X. Always plus B squared. 4 times 4 is 16. That's your answer. All right. We're going to modify number 10 here. Let's go ahead and put a 20. Hold up. Before I make a grievous error. Yeah, we'll put 27 there. Put a 27 on that. Just so we can see what to do if there's a coefficient. All right. Cube roots, again. Take a cube root of the whole thing. Cube root. All right. A, the cube root of 27 is 3. The cube root cancels the cubed X. B, the cube root of 343 is 7. Now we put these in the SOAP formula. So first set of parentheses is A, 3x, same sign as the problem, plus 7, parentheses. Now A squared, 3x times 3x, 3 times 3 is 9, x times x is x squared. Opposite, so that's a plus, so minus. A times B. 3 times 7 is 21. Bring down your x. Plus, because it's always plus, B squared. So 7 times 7 is 49. And that's your answer. See, even with the coefficient, it's not bad. All right. Let's talk about some GCFs. What did we do with the GCF before? Well, we took it out. So we're going to do the same thing here. Let me just go ahead and double check what the GCF is for the first problem, though. I just want to make sure before I goof you all up. Well, it's not 9. I bet it's 3. It is 3. So we're going to take a 3 out of both of these because 3 goes into 192 and 81. So 3 goes into 192. Hang on. Put my 3 out front. It's my little brother. I can't forget it. 3 goes into 192 64 times. Bring down your x cubed because we didn't take out any x's. 3 goes into 81 27 times. All right. Now, we're going to do the SOAP formula on just the inside here. So we're going to take our cube root on both terms. The cube root of 64 is 4. And the cube root cancels the cubed on the x, and we have just x. B, the cube root of 27, is 3. Bring down your 3. It's your little brother. You can't forget it. So we're going to have A, same sign as what's on the inside, B. Then we're going to have A squared. 4x times 4x. 4 times 4 is 16. X times x is x squared. Opposite sign, so that's a minus. We're going to put a plus. A times B, 3 times 4 is 12. Bring down your x. Always plus B squared. 3 times 3 is 9. And there's your answer, including the GCF of 3 on the front. All right, last question. So on here, we're going to take out our GCF. And let me just verify the GCF really quickly. Is it 4? Does 4 go into 108? Of course it does. All right, it is 4. So we're going to take out 4. And you're going to say, Mr. Barton, how did you know it's 4? It's practice. I just know my times tables very well. And then this has x's, and so does this. So we can take out 1x because the smallest exponent is a 1. So we're going to put 4x in front. We're going to divide. 4 goes into 32. How many times? 8. We had 4x's. We took one out, so we're going to have 3 left. Plus 4 goes into 108 27 times. We had 1x, we took it out, so there's no x there now. All right. Now, cube root of the inside, because these are both perfect cubes. So a, the cube root of 8 is 2. The cube root of x cubed is x. The cube root of 27 is 3. So we're going to bring down our 4x because it's our GCF. Parentheses. A, same sign as the problem, b. Then a squared. 2x times 2x is 4x squared. Opposite sign from the problem, so minus. A times b, so 2x times 3. 2 times 3 is 6. Whoops. 6, bring down your x. And then b squared, always plus 3 times 3 is 9. And that's our answer. So we learned 2 new formulas. We practiced with perfect squares and perfect cubes, and we learned to factor. Hopefully, with the rapid fire examples you just watched, you've learned how to do that. If you think you're going to struggle a little bit, or you're still not really sure how to tell what the signs are or how I'm getting all these numbers, please ask me. I would love to help. I would love to help during class even. So let me know if you need any help. Otherwise, have a splendid rest of your day.